because you have become matured, we will just have some convention, so that we can write the propositions by reducing some of the parentheses, right. So, it is something like giving a precedence rules in programming languages. Even in mathematics you have used it from your childhood. Suppose you write say a b plus c d in usual mathematics, then you would think it as this, right. Okay. If you put the parenthesis, it would look like this, but certainly not as, right, not like this. So, it is because multiplication has higher precedence than the addition. So, this is what we mean by higher and lower precedence. Similarly, we will define some precedence for the connectives, so that number of parentheses will become less. It will not eliminate it altogether, but it will be less in number, fine. So, for the precedence we take not as the highest precedence. So, next precedence will be for these two connectives. So, once we say both of them have the next higher precedence, what about comparing between them? So, we will put them of equal precedence. So, you see that parentheses are not altogether eliminated, right, some might be there still. So, write they have the same precedence. Similarly, the next two connectives, they have the lowest precedence. Right. So, these having equal precedence means among themselves. Let us see one example how this goes. Now, it is not really readable, right. We need some parenthesis. So, one parenthesis we will keep here, that will say that even if they have the equal precedence, we know how it has been formed. First Q and R has been formed, next P has been added and OR together, right. So, you can have another parenthesis here, okay, but we do not need it because implication has the least precedence. So, rather we need a parenthesis here, okay. Well, we can have it this way, but without it there will be again problem, because even if not has the highest precedence, it will take with R now. Instead of this, suppose you have inserted here, it would say that first R if and only if Q been formed, then not has been added, right. So, they will have different meaning now. So, this is how precedence will be used, and some less number of parentheses we can use after this, fine. Now, let us come back to our relevance thing, that if a variable is not occurring in a formula or a proposition, then it does not matter what value you assign to that variable, fine. So, let us formulate it first. It is called the relevance lemma. Well, let W be a proposition, let VW, V subscript W be the set of propositional variables occurring in W. So, what we want is if some propositional variable does not occur in VW, is not a member of VW, then I of that propositional variable and j of that propositional variable, even if they differ, I and j should give the same value to W, right. So, you put it the other way, if I and j both agree for all the propositional variables in VW, then they should agree on the whole of W, right. Is that okay? So, what we will be writing is, let I j be two Boolean valuations that agree on VW, right. They should be equal for each propositional variable in VW, that which are occurring in W, fine. So, such that I of p equal to j of p for each p in VW. Is the scheme clear? So, I and j agree on all the propositional variables occurring in W, that is what it says. Then what should they have? They should agree on W itself. Then I of W must be equal to j of W. Is the formulation clear? So, that if they do not occur, some propositional variable does not occur in W, it does not really bother us, fine. Now, once you understand the proposition, we should prove it. So, how do you prove? Proof will be by induction, on, we make that standard. Nu W means number of occurrences of connectives in W. So, first the basis case when nu of W equal to 0, fine. So, in the basis step, say nu of W equal to 0. So, in that case what could be W? There is no propositional variable occurring in it. What could it be? It is not propositional variable, it is the connectives, right. Nu W is the number of occurrences of connectives in W. If there is no connective, what could be W? It has to be atomic. So, atomic means what? It can be propositional constants, top, bottom, or it can be a propositional variable, fine. So, if it is top, it is a propositional constant, I of top is always equal to j of top. Is that clear? If it is bottom, then that is also same, it is equal to 0 now instead of 1. So, let us write that first, then W is equal to top or bottom, or W is in, let us write some VW, maybe we can write, but we may say W is a propositional variable, that is easy. Fine. If W is top, then I of W equal to j of W equal to 1. If W is bottom, then I of W equal to j of W equal to 0, fine. If W is a propositional variable, then what happens? Then VW has only one member, which is W, right. So, VW is equal to W itself, and by the assumption I of W equal to j of W, assumption of the statement. that I and j both agree on VW. In VW there is only one member, on that they agree. So, I of W must be equal to j of W. So, this clears the basis step. Now, in the induction step we lay out the induction hypothesis. Suppose for all propositions u with nu of u less than n, okay, we have I of p equal to j of p for each p in VU implies I of u equal to j of u. This is the induction hypothesis, right. Then we start with, let W be a proposition such that VW, well we need really for nu of W is equal to n, fine. Number of occurrences of connectives in W is n. Then how to write W? By definition of the grammar of W or all propositions, we say W must be is not x or x and y or x or y or x implies y or x by conditional y for some x y propositions with nu of x less than n, nu of y less than n. Okay. Now, you can complete it. Yeah. Let us see the first case. Suppose W is not x. Now, it has n, nu of W is n. So, nu of x is less than n. Now, apply the induction hypothesis, I of x equal to j of x. Is that clear? Because all the variables that are occurring in x, that set is a subset of variables occurring in W. So, you can apply the induction hypothesis. Okay. Now, what happens? I of x equal to j of x, then by definition of not, I of not x is j of not x, all the things go similarly. Is that clear? In fact, there is nothing more to it than telling that the Boolean valuation can be extended uniquely, and that is because we have proved the unique parsing theorem. Is that clear? Yes.
Having the x and y have all the brackets in it without going by this precedence rule.
Yes, we are not using the precedence rule.
Okay.
We are doing
so it is non-ambiguous.
But even if you use precedence rules, it is unambiguous because of the precedence rules.
Within the same precedence, like,
There will be brackets,
okay.
right?
So
Still it is unambiguous, but we are not proving unambiguity using the precedence rule. We are just using it as a shortcut to write our original formula, original proposition, right? Then what it says is, if you consider an interpretation or you consider a Boolean valuation, you need not consider how it assigns the propositional variables which are not occurring in a formula, in a proposition, fine. So, if that is so, then we are only concerned with the propositional variables that are occurring in W, all the elements of VW only, fine. So, suppose there is W which is a proposition having two propositional variables, then we can consider only 4 number of possible truth assignments. We need not consider any more, fine. In fact, there are infinite number of truth assignments, because P3 which is not occurring in it can be given 0 or 1, P4 which is not occurring in it can be given 0 or 1, and so on. So, it can be potentially infinite. However, this allows, relevance lemma allows us to confine ourselves to only those 4. That is why the truth table method succeeds. Is it clear? So, all those truth assignments or the Boolean valuations having only VW in its domain, right, are called interpretations. So, we can use the interpretations instead of the general assignments or Boolean valuations, fine. So, that is the clue from the relevance lemma, that we can always confine to the interpretations. But there is a problem. Say you have a formula x which is not having an occurrence of a propositional variable p. There is another proposition which is y where p occurs, fine. Now, you have w which is equal to x and y. Previously, you had interpretation for x which did not give any assignment to p. You had another interpretation for y which has assigned something to p. Now, for w your interpretation should also consider the assignment for p, right. So, when you say it is interpretation, it is really interpretation of a given proposition. In that sense only we can talk of interpretation, but usually we forget it, we do not mention the proposition, we say an interpretation. It means in the context whatever propositional variables are considered, we take them all. Is it clear? That is a sloppy language used there. So, we have to be cautious about it, that is what it says. Okay. Let us see some example how the interpretations are used. Consider a proposition which is a W which looks like this. Okay. We want to evaluate it under various interpretations. Now, first we have to find out which are the propositional variables. Look, neither p is a propositional variable formally, nor q is a propositional variable formally. We have only p0, p1, p2 and so on. Okay. So, by writing this, we are again making some convention, that instead of writing p0, p1, p2 and so on, we will write pqr. Okay. So, because it is always difficult to write with subscripts, we will simply proceed with this, use different symbols rather. So, now let us say p, q, r are the propositional variables occurring in this proposition. So, since there are 3 in number, there will be 2 to the power 3 or 8 interpretations, fine. All the interpretations can be written down by varying over 0 and 1. So, let us write them. Say for p, I have now 0, 0, 1, let me take one more 0, okay. And for q, let me write 0, and for r, so now you are required to read the rows. So, first row says it is an interpretation which gives 0 to p, 0 to q, 0 to r. Next row says it gives 0 to p, 0 to q, 1 to r. So, there is some difference, right. So, that is how these are 8 possible different interpretations in this context, fine. Now, instead of making a bigger truth table, what we do, we will make it a shorter one. We rather repeat on the same propositional variable whatever interpretation we are having. So, let me repeat this column p under this p as it is. We have to be truthful. You may not repeat, but we have to make a bigger truth table later. I want to make the truth table shorter by repeating this. Similarly, for q, I will again repeat here under q. Okay. Next, I want to go for evaluation of the connectives. So, now not p, this is one interpretation where p is assigned 0, so its negation will become 1. So, I will write it under this not, under this connective. That is how it will go. Okay. Now, when you take not p and q, precedent says it is not to be interpreted as not of p and q, it should not be. What it means is not p first to be evaluated, then that along with q should be ANDed together, right. So, that means with this one first column and the third column we have to follow the rules of AND, fine. So, that becomes 0 here, I will write below it 0. Is it right? AND becomes 1 when both of them are 1, otherwise it is 0. Next, I have to do similarly here. Now, first not q, so that changes the truth values. Okay. Now, if and only if between this column and the last but one column, that is your not q. So, that becomes 1 when they are same, otherwise they are 0, right. So, this becomes 0 and 1, that gives 0, 1 1 is 1, 0 0 is 1, all right. Next, p will be ORed together with this if and only if, fine. So, I have to consider this column along with this column and OR them together. So, OR will be 0 when both of them are 0, otherwise it is 1. So, that gives 0 here. All right, just check them. Fine. Next, we have implication between this whole thing and this whole thing. So, this whole thing is written under this column and this valuation is written under this column. So, these two columns we have to take and perform the implication. Implication is 0 when its antecedent is 1, consequent is 0, right. All other cases it is 1. So, you have to search for 1 0, give that 0, all others will become 1. Zero here. Is that right? Fine. So, that is how the truth table will go. So, what does it say us? Why the truth table at all? Well, it tells if I is an interpretation which assigns p to 0, q to 0 and r to 0, then that I assigns this whole proposition to 1. This is what it says, fine. Similarly, if you say, let me say this is I and this is j, this row. So, this says if j is one interpretation which assigns p to 0, assigns q to 1 and then r to 1, then it assigns the whole proposition to 0, fine. Now you see there can be various possibilities of assignment of 1s and 0s to any arbitrary proposition. So it might quite happen that after you complete the truth table you get everywhere 1, right, you may get everywhere 0, or you may get something like this, some rows it is evaluated at 1, some rows it is evaluated as 0, right. So you want to give different names for all these things, fine. If you go back to our definition of models, it says one Boolean valuation I is a model of a proposition W if I of W equal to 1, fine. Due to relevance lemma we can say that instead of Boolean valuations only interpretations can be used. So you may say a model of a proposition is one interpretation which satisfies the proposition, fine. For example, if W is this proposition which we have considered, then I is a model of W, I is an interpretation which assigns 1 to W, but J is not a model of W, fine. Is it clear? Now if we say W, then W has many interpretations which are models, and W has one proposition, one interpretation which is not a model. For example, J does not satisfy W, fine. So what we say is I satisfies W, there exists one such I, therefore W is satisfiable, it is satisfied under some interpretation, fine. So we just give definitions which arise from this consideration. We say that W is satisfiable if it has a model, which means there exists an interpretation which evaluates W to 1, fine. Now you are using high level languages, instead of telling I of W equal to 1, just say it has a model. Then we say that W is valid if each interpretation satisfies it, right, if each interpretation of W is its model. Right. So had this J satisfy W, you would have told that W is such a proposition, right. So here whatever W you have taken is not valid, right, but you can give examples of valid propositions. For example, P or not P, right, it will be valid, but there is another basic thing which is valid. Can you tell me what it is? Top is a valid proposition because every interpretation of it evaluates it to 1 by definition, okay. And bottom is invalid and also unsatisfiable, right. So we say that W is invalid if it has a non model, right. There is an interpretation which falsifies it, which does not satisfy it, if it has a non model. Okay, which means there exists an interpretation J of W such that J of W equal to 0, that is what it says. So sometimes we write, to say that it is not a model, we write J does not satisfy W, or j falsifies W. These are also some different notations and some different way of reading it. J falsifies W or j does not satisfy W. We say that W is unsatisfiable if what happens? If it does not have a model, it has a non-model, it does not have a model are different, right. You say it has a non-model means there is one who is falsifies it. It does not have a model means each interpretation falsifies it, right. So, if each interpretation falsifies it, okay. But there will be some which are neither satisfiable nor valid. Can be? Can there be some propositions which are neither satisfiable nor valid? They are unsatisfiable, right. If something is not satisfiable, then invalid, right. So, unsatisfiability implies invalidity. For example, you take bottom, fine, but there can be also some propositions which are both satisfiable and invalid. For example, this, right, it is satisfiable because I is a model of it, it is invalid because j is a non-model of it, okay. So, such propositions are called contingent propositions. Contingent means having some information content, right. Valid propositions and unsatisfiable propositions have no information content, though we are more interested in them. They do not have any information content because either they are always true or they are always false. So, we add nothing by knowing that something happens which is of that category. Like your friend comes from outside, you ask him, is it raining outside? He says it is either raining or it is not raining, right. He is true, he is valid, that statement is valid, but it adds no information, it gives nothing to you, right. So, these valid propositions have no information content, but if he says it is raining, so that means he is asserting one contingent proposition. So, that now creates a world, a different world which gives you some information, okay. That is why these models or interpretations they are also sometimes called worlds because of this. When you come to modal logic, you will use this terminology always, worlds, not interpretations, okay. Let us continue with this. So, though they do not have any information content, valid propositions and unsatisfiable propositions can be used for something else, to find out what else can be concluded from this given things, what else can become equivalent to this, and so on. So, if you go back to your definition of equivalence, you will see that you can express it through models now, fine. So, recall we say that u is equivalent to v if I of u equal to I of v for every Boolean valuation I, right. Now, you can think of interpretations. So, that means u and v are equivalent if their models coincide. Each model of u is a model of v, each model of v is also a model of u, right. So, we can take it as a definition now, say u is equivalent to v if each model of u is a model of v and each model of v is a model of u. Fine. Then it should be very clear that u is equivalent to v if and only if u if and only if v is valid. Is that okay? So, to write that it is valid, we just have another symbol before it, the same symbol exactly we are using for models. We are overusing the symbol. Okay. Once more we will overuse it, then you will see why all those three will become the same. Okay. So, to say that a proposition is valid, instead of writing is valid on the right side, we will just give a prefix of it. We will write this new symbol here, models, right, which we are writing for models also. We will read it as U if and only V is valid. Now, how do you see the truth of this statement? So, suppose we use that each model of U is a model of V and each model of V is a model of U. How does it say U if and only if V is valid?
Each interpretation should give the same.
Consider any interpretation. Okay. Then
Either both U and V of are models or they are not for that interpretation.
because U is equivalent to V, right. So, once it is a model of U, it has to be a model of V, it should evaluate that as 0 also, it is not possible. Once it evaluates 1 to or U to 1, it has to evaluate V to 1 also, fine, and conversely. So, both the things are same, or you can get it from the truth table directly, it is the same way, right. It will take only 4 lines, though P and Q are not propositional variables, you can still have a truth table, because under any interpretation U gets either 0 or 1, similarly V gets either 0 or 1. So, there are really 4 possibilities. It is not a truth table in the sense of starting from the propositional variables, right, but it is just some 4 cases, we are showing it in a truth table, fine, and then you can conclude about it easily. Is that clear? Now, similarly you can see that U is valid if and only if U is equivalent to top. Can you see that? Once you say U is valid, you consider any interpretation, it is a model of U, right. So, any interpretation is a model of which formula? Of top, and conversely, fine. Now, you can say U is valid if and only if not U is unsatisfiable. Can you see this also? So, you start from the left side, U is valid. So, now consider any interpretation, you want to show that it is not a model of not U, right. You start from left side, now you want to show this, consider any interpretation I, right. Now, because it is there, I is a model of U, so I is not a model of not U, right. For each interpretation it happens, therefore not U is unsatisfiable. Conversely, suppose not U is unsatisfiable, now you want to prove U is valid, start with any interpretation, that interpretation since not U is unsatisfiable evaluates not U to 0, so U to 1, it is a model of U, right. Similarly, you can say not U is valid if and only if U is unsatisfiable. Same argument. Let us take an exercise, whether this is valid, unsatisfiable or contingent. Yes. Well, it is not difficult for you. You have come through many more hurdles. So, just 8 lines you have to make, assigning 0 and 1s. There are 8 interpretations. Now, verify whether what happens for the interpretations independently. Fine. Well, I will try to have a shortcut here. Okay. So, suppose I is an interpretation, let me call it W. I is an interpretation which is not a model of W, right. Interpretation such that I of W equal to 0. Okay. Because implication is easier to evaluate for zeros. There is only one case when it can be 0. Its antecedent is 1, consequence is 0. That is why I am trying this first. Okay. So, in that case, its sub proposition, which is P implies Q implies R, should be 1, and the other sub proposition P implies Q implies P implies R should be 0, right. So, then I of P implies Q implies R is 1, I of P implies Q implies P implies R is 0. Now, again I take up this case first. This will give me 3 cases, this will give only 1. So, let me take this case. So, this says I of P implies Q should be 1 and I of P implies R should be 0. Now, again I take up this case, this is only one case, which gives me I of P is 1, I of R is 0. Okay. So, now I get P is 1, R is 0. If P is 1 and P implies Q is 1, what can be Q? It can't be 0. If Q is 0, then it should have been 0, but it is 1, therefore, Q must be 1. So, this says I of Q is 1. Okay. So, now I get P as 1, Q as 1, R as 0. Okay. So, what about this? P is 1, Q is 1, R is 0. So, Q implies R should be 0, right, but P is 1, therefore, this should have been 0. So, this says I of P implies Q implies R as 0, but it is given to be 1, there is the problem, right. So, it can't happen. Okay. It says this is not possible, I of W can never be 0, whatever interpretation I may be, therefore, W is valid, because there is no interpretation I which falsifies W, therefore, every interpretation satisfies it, therefore, W is valid. Is that clear? Now, if one proposition is valid, then it has to be satisfiable. Yes? Why is it so?
All its models should satisfy it. So, there exists at least
Models always satisfy.
I mean, all its interpretations should act as models. So, there should be
Yes.
at least one interpretation which acts as that model.
From all to some, when you come, there should be at least one interpretation, right? Otherwise, you can't conclude it, right? All interpretations are models, that is why it is valid. Then you want to conclude some interpretation is a model. This you can conclude provided that all is not vacuous. right. It might happen that a proposition is there having no interpretations, then all its interpretations are models, right, but that is not the case. Every proposition has at least one interpretation. Is that clear? Is clear or not? Every proposition has at least one interpretation. How? See, a proposition suppose has a propositional variable in it, then assign that propositional variable to something 0 or 1, that shows that that proposition has one interpretation. But suppose there is a proposition having no propositional variables in it, for example top, what is the interpretation then? Yes, there is no propositional variable occurring in it. So, you take by default any assignment, any truth assignment. There are plenty of truth assignments, right, and top is equivalent to every valid proposition, right. So, you can think of top as P or not P, I of P equal to 1. So, now this is a convention we are going to put to conclude that, right, that top and bottom have interpretations, that is the basic thing. Otherwise, you cannot show that there exists always an interpretation of a proposition.